Welcome to our Malvern Mastersizer 3000 presentation, the latest laser diffraction system from Malvern Instruments. Today we'd like to introduce you to our new Mastersizer 3000. For many years, laser diffraction has been the dominant particle sizing technology used in many branches of industry. This is because it's easy to standardize, it's robust, and measurements are quick. A laser diffraction system essentially consists, of course, of an optical bench. And here we have a much smaller footprint compared with our previous model. The bench space needed is 70 centimeters long, 45 centimeters high, and a total depth of about 60 centimeters, including the modules. Here you can see the optical bench. It contains two light sources. At the bottom of the measurement system, we have a helium neon red light source. The laser beam is folded back on itself and transported through the sample cell. This is our powerful blue LED, with which we have achieved greater sensitivity in lower measurement ranges, so that, if the sample lets us, we can make reasonable measurements even in the range below 100 nanometer. The cell sits here in the laser beam, and the detector itself is completely isolated from any contact with the sample. We've been using this modular concept at Malvern for many years. In other words, we operate with dry units, like our Aero S module here, and with various wet units, like the new Hydro MV for medium volumes shown here. About 100 milliliters are pumped around here. This is our LV module large volume, about 600 milliliters are pumped around here. And a single unit, or EV module, with an exchangeable beaker for versatility. That completes our hardware components so far. As you know, a laser diffraction measurement firstly relies on proper sample dispersion. As a rule, we're dealing with agglomerated materials, with suspensions, emulsions, and dry powder samples, and we need to disperse these agglomerates without changing the particles themselves. In order to achieve this important goal, we offer control dispersing features in each module. A measurement is made in two steps. If the products are not known, we generally conduct a method development step. We've connected up the wet unit MV, and I'd like to begin with this. We're going to measure a nanosphere standard, approximately 100 nanometers in size, which will now be the next step in our presentation. After starting the software, we see this screen. Along the top are the usual window icons. Create a new file, open an existing file, save the file. Later then print out a result or save as a PDF. These areas here are not yet populated because we haven't generated a measurement result yet. Here are the two options with which we can make the measurement. Either an existing SOP is called up, in other words a standard operating procedure, or we perform a manual measurement, an option we want to use later for a method development. It's possible for various reports to be selected, edited, created, and finally for the data to be exported. We'll now start the manual measurement. Here the entire procedure with measurement parameters and information about our sample is shown. We start by identifying the sample, by entering the name of the sample. We want to measure nanospheres, and so we enter the appropriate description. In the next step, we select the particle type. Here we can use the Mie theory or the Fraunhofer model for our evaluation. Both options are available in the equipment. We measure a nanosphere whose Mie parameters we already know. We can therefore use the Mie theory for our evaluation, so we select it here. These are the available optical parameters such as absorption coefficient and refractive index, which we've already entered. We are working in water. This means we're dispersing the latex in water, and we enter that here. If necessary, we can display instructions before and/or after the measurement, but we don't want to do that now. Now to the measurement itself. The measurement is divided into a background measurement and the actual measurement, the data recording. We're dealing with a very fast measuring system. The Mastersizer 3000 measures at 10 kHz, and data is therefore recorded very, very rapidly. It's therefore sufficient to work with a rough measurement time of 5 seconds. The same applies to blue light. Here then also 5 seconds of background measurement and 5 seconds of data recording. The measurement sequence can be set. We enter 3 measurements here, without a delay between the measurements, which we could specify if required. The next option is the light obscuration. This means that laser diffraction always requires some amount of signal. There should be not too few particles, but also not too many in order to avoid multiple scattering. Here we enter a lower limit of 1% and an upper limit of 20%. Here we have the pump speed, the stirrer speed, which we set at 2000 revolutions per minute. The tank will be filled automatically since we're connected directly to a water supply, and we can select various cleaning cycles, from short via thorough to user-defined cleaning cycles. We'll select short cleaning. We now come to the data processing. Here we have various analytical models to choose from. In the case of an unknown sample of Y distribution, we will select our general purpose model. If we are measuring a latex standard, we will select our latex analysis model. If necessary, here we can somewhat limit the result. The result is presented as a volume distribution, which is indeed what laser diffraction delivers. It also can be converted into a number distribution if desired. If necessary, we can enter our own user size classes. After the measurement, we can navigate to the data export option and transfer the data to Excel, for example. After multiple measurements, we can take the average of the results here, print out the result, or send it, for example, as a PDF file electronically by email. This deals with setting the measurement parameters. Now we switch to the cockpit view of our measurement manager. All information which we need during the measurement we can see here on this screen. Here on the left-hand side is the laser intensity meter. This displays the laser power where the obscuration will be displayed later during measurement. Here is detector intensity display with the particular signals associated with channel. Then after the measurement, the display of the resulting particle size. And here at the bottom, very helpful during method development, are trend view. For example, if 5 or 10 measurements are made one after the other, they appear here in series. If any measurement parameters are adjusted, like here for example, ultrasound application or stirrer speed, any resulting changes in the sample are seen immediately. In this region here, the instrument can also be emptied or automatically filled, but this is also directly available afterwards in our progress indicator. I am now going to make the machine ready for measurement and connect the disperser. You can see here the 2 hoses. Flow into the cell, return into the module. We will look at the cell in more detail later. We start by initializing the equipment, essentially an alignment check. We perform a background measurement, one for red light and one for blue light. In the next step, we will introduce the sample. The obscuration display at the moment is at 0%. I am now introducing some of the sample, and we can see how the obscuration bar rises. We now start the measurement. We look at this as soon as the first measurement is available. Our first values are also available here in the trend display. We plot here the dV10, the dV50 and the dV90. And then already obtain the resulting particle size distribution. Here's the second measurement, and the second result. The average of the two results is taken immediately, and this average is displayed as well as the relative standard deviation. After the third measurement, we apply the ultrasound to see whether the sample is affected by this and whether there are agglomerates in this sample. We would also label this accordingly with ultrasound. We start the ultrasound and measure the sample 3 more times whilst it is being sonicated. Here already is the 4th measurement, and we can see hardly any difference from the first 3 measurements. And so it goes on. Here's the 5th measurement. We stick closely to the recommendations of ISO 13320 for laser diffraction by keeping exactly to the guidelines during the method development. We switch off the ultrasound again and perform 3 more measurements without sonication. From this trend display, we can now deduce the conditions with which we want to perform all further measurements in the future. The SOP is also created from this result. In our case, the SOP is very simple because of the constant values. After the sample has been measured, the system is now cleaned as a 4th step in our cleaning cycle. We drain off the liquid, and then everything is disposed of in our waste container. Thanks to the very powerful centrifugal pump here inside the instrument, we can empty everything, leaving almost no residues. If necessary, we can follow up with a 2nd rinsing cycle. Although the cleaning performance contained within the system is already very effective. As the liquid is drained off, the speed is increased. You can see here the measurements that we made, and these can also be viewed individually. This is how a report would look later. We can also overlay all the results. These are, of course, distributions which coincide. The graph can also be changed if required, using the option histogram and undersize, for example. As I said, there are no major differences in our measurements, which means we can choose a measurement and create an SOP from this. Here I'm marking the corresponding measurement. Using the right mouse button, I call up this menu and select the option Extract SOP. The SOP editor is displayed, and this measurement procedure can now be saved as an SOP for nanospheres. My measurement method for future nanosphere measurements has therefore now been laid down. We now close the window, save once again our changes, and navigate back into the measurement window. As we can see, the cleaning cycle is now ended, and we can see in the background that the instrument has been cleaned and is ready for measurements again. We close the measurement window and now want to perform our SOP, which we've just set up. Here is our nanosphere SOP. We select it now. Here at the top, we are given the instruction to press the Start button for the measurement to start. Here again are the sample nodes we entered. Initializing the equipment. An alignment check by the instrument. Then onto the background for the red light source, for the blue light source. Now we introduce sample again. On the left again, the light obscuration, which is now slowly increasing. We land again just above 1%. If the obscuration is within the desired limits, this is recognized in the SOP and the measurement is started automatically. We've selected 3 measurements, from which we could obtain an average again. However, since the differences between the 3 measurements are so small, we can omit this step in this case. As before, here at the bottom in the trend display is the first result. Now the second result. Now all 3 measurements have been performed. The instrument puts itself in the cleaning mode, rinses itself, and so on. We can now leave this area of the program and take a look at the results. These are the last 3 measurements which we can mark. Here in the overlay too, there is a very low standard deviation, as is to be expected with such a sample. The reports our software has compiled also contain information about the data quality, as is the case, for example, with the ISO compatibility check. The ISO standard specifies certain limits with respect to the D10, D50 and D90 values, if we perform several repeat measurements. In this case, the last 3 measurements would be marked. The values updated, and we can then see whether we are within the ISO limits. Our result shows that in this case we are within the ISO statistics, and the display is accordingly green here. That's all on the subject of wet measurement. Let's now turn to the subject of dry measurement. During dry measurement, the desired effect is that our agglomerated particles will be successfully dispersed. We have to deal with 3 effects here: particle-particle collisions, particle-wall collisions, with pipes, redirection of the particles on the way to the cell, and, because of the turbulent particle movement, shear forces which also enable particles to draw apart. The aim in dry dispersion is to only disperse the particles and not to destroy them. For this, Malvern have developed completely new Venturi nozzles, which can be inserted into our Aero-S module. An important point: these Venturi nozzles can be easily dismantled. For example, if you're using products which may tend towards caking, the Malvern Venturi nozzle can be quite simply taken apart and cleaned. Here is our standard Venturi, which I'm going to install in the instrument. With this standard Venturi, compressed air is passed in from the bottom and is then deflected to the side, as a result of which our powder, which is introduced at the top, is simply carried along. This means that the powder can be dispersed very gently. Loose agglomerates are broken up, but the particles are not destroyed. This development is particularly important for our pharmaceutical users, because crystalline pharmaceutical active ingredients can be very easily destroyed. With the help of the gentle dispersing, this type of sample can also be measured cleanly. Here is the AeroS module, which I am now going to install in our Venturi nozzle. I open the shutter and first remove the vibrating tray. Here on this vibrating tray, the material feeds down here into our funnel. Everything can be dismantled completely without any tools. The module is now also being converted. The pump must now also be disconnected from our wet dispersion unit. Now the switchover. First, the wet measurement cell is removed. You can of course also remove the hoses here, but this is not necessary. If the wet measurement cell needs cleaning because the measurement windows have not been cleaned during rinsing, we can very easily take these apart by turning the lever to the right. We already have one half of the cell in our hand and can clean it. The same applies to the other side. We then put it back on and close the lever. We now place the wet measurement cell to one side. This is the dry measurement cell, which we now want to insert. The principle is the same here. Easy to remove if the window has to be cleaned. This is done very quickly, as you can see. Cleaning is not of such great importance with dry measurement, especially since sheath air from the outside is sucked in. This air forms a sort of curtain in front of these windows, and contamination can therefore be as good as ruled out. We now insert the cell. The cell is positioned again automatically. We push the module here in front of the cell and connect the flexible hose pipe to our module. That was all we need to do to change from wet to dry dispersion. The software has also already recognized the changeover. Here at the bottom the display is green, which confirms that the AeroS module is connected. We could now complete the same steps as before, that is to say, manual measurement, and then method development. These are basically the same steps as those we took before in the wet measurement. Most of the procedures are repeated. The only difference is that in dry measurement, we do not use ultrasound for the dispersion or operate with a stirrer output that can be varied. Our dispersion setting here is the compressed air pressure. The higher this value, the greater the forces acting on the particles. This is how we vary the dispersing power, and the transport rate indicates the extent to which the vibrating tray is agitated, so that the material is transported in the direction of the Venturi nozzle. We now miss out the method development and go directly to the SOP measurement. We close this window and we start the dry SOP. We activate the option Execute SOP. In this case, we are now measuring a glass bead sample. A somewhat broader distribution. Poorly disperse. And then we start this SOP. Here the first information, the request to fill the tray. We take our sample, open the lid, and introduce approximately 2.5 gram directly here at the top. It's of course possible to measure more or less material. Starting from tiny amounts up to approximately 50 milligrams, we can top up continuously at any time if here at the top the opening is left free. We have now filled the sample and start the measurement procedure. Here, once more for safety, the question is being asked if everything is set as it should be, which in our case is yes. The vacuum extraction system is now switched on. Compressed air is introduced, and of course it is checked that the values for the vacuum performance and air pressure are constant. We now perform our alignment check again. Now the background measurement. Now the vibrating tray. This means that the material falling into the funnel is carried along by the air, blown through the cell, and is collected in the vacuum extraction system. The sample is now finished. After a short waiting time, the measurement is stopped and the result is displayed. The system is cleaned, that is to say the vibrating tray is shaken vigorously once again to shake off any particles which may still remain stuck to it. To ensure that no further residues remain in our system, once again air is blown through under a high pressure. Here also the result can already be viewed. Here is our result. Under single result on the report page, we can then also see for ourselves the size distribution. That completes the measurement procedure. If we want to convert the system back after a dry measurement, we have to perform the same steps in the reverse sequence. For this, I first undo this connection here, pull the module over and open the lid. We can then also pull out the sieve and check whether it's clean enough, which is the case here. Here then is the vibrating tray, which we can pull out. Also no residues to be seen. After pulling out the vibrating tray for cleaning purposes, we can of course also pull out the Venturi, and if necessary dismantle it still further by unscrewing it here. These parts, by the way, are made of high-grade steel, but there is also a ceramic version for abrasive materials. As you can see, it's very easy to clean the parts. I'm now screwing the assembly back together. There's also a second Venturi, which I'd also like to show you. Our high-energy Venturi, which is built in just the same way as the standard unit. However, this Venturi additionally also has a 90-degree angle, which acts like a baffle plate against which the particles are fired. This provides a further additional dispersing power, and this Venturi is used for very adhesive particles, so that we can also achieve a good dispersion of these materials too. That completes our practical part. What I would like to show you now is the transfer of data to Excel, for example. This is a relatively easy matter and functions as follows. To give an example, if you want to transfer these three measurements here, you mark the entries in question and navigate top right to the option Export Selected Records. If you wanted to, you could of course export all the measurements. In the Export Data window, there are various export templates. A standard template containing, for example, the record number, the sample name, the measurement date, and further numerical values, that is to say more or less what we have available here at the top. However, we can also create our own templates. Like here, for example, result under. That is to say the undersize plot. We have here the option between column and row presentation, and can choose between commas and tabs, which we need here in our case. We go into the Windows clipboard, switch to Excel, and then insert the record set in question directly here using the paste function. In the individual size classes, we now have our numerical values. As you can see, transfer of data is relatively simple. Now that we have transferred data, I would also like to show you how a report is compiled, either as hard copy, as a printout, or as a PDF. For this we have our Report Designer, a tool with which we can compile individual reports. As I am now going to show you, you can start from an existing report and modify this as required. For this, select the Edit option and look at the current fields and values used. You can change the parameters of these fields as required. To give an example, if you want to modify the DV90 value, you would click on the appropriate entry and would navigate to the required value in the list.
Dementsprechend hier verändern. Springen wir gerade mal zu der Anzeige. Zum Beispiel jetzt anstatt.
Here I'm changing the DV90 value into DV80, for example, and could now store the entry under a new name, as a result of which we would also have available a new report with a new parameter value. However, we are not changing our report now.
Und hätten hier also unsere Reportseite und
we now want to look at our current report page in print preview. This is how your report would look like after a measurement. Notes, instrument setup, results, averages, the size distribution and the size results, all on one A4 page. If required, we can add here to the report our SOP settings, or generally the settings which have now been used for the measurement. We therefore have all the important data summarized on this page. And can use this as an attachment to an existing report. With the report, we therefore have available not only the data for the measurement result, but also the detailed data on the particular equipment setup. I've now come to the end of my Malvern Mastersizer 3000 presentation. Thank you for your attention and for watching. Finally, don't forget our homepage is malvern.com and our Malvern head office in the UK. We would be pleased to hear from you again. Thank you.